Imagine yourself floating gently above a world so different from our own that time itself moved to an entirely different rhythm. Close your eyes for a moment and picture this ancient Earth, some 4.5 billion years ago, when our planet was young and full of quiet possibilities. The sun rises not in the familiar arc you know, but glides across the sky in a swift, gentle dance, transforming dawn into dusk in what we would now call merely 3 hours. This is not a tale of sudden changes or dramatic transformations, but rather a soft story of how time itself has evolved, how the cosmos has shaped our world through patient, persistent influence, like water slowly smoothing stones in a peaceful riverbed. Let us drift back together through the gentle mists of deep time, floating weightlessly through the ages, back to when our planet was newly formed from the quiet gathering of cosmic dust and ancient starlight. The Earth then was not the blue marble we know today, but a warm, softly glowing sphere, still cooling from its birth in the stellar nursery, radiating a gentle heat like embers in a dying fire. The moon hung much closer in the sky, so close that if there had been eyes to see it, it would have appeared enormous, filling a substantial portion of the heavens with its silvery presence, like a guardian watching over a sleeping child. In this primordial time, our world spun with a gentle enthusiasm that made each rotation, what we call a day, last only 6 brief hours. The mechanism behind this rapid rotation is beautifully simple, yet it speaks to fundamental principles that govern everything in our universe. When Earth first coalesced from the swirling disk of material surrounding our young sun, the conservation of angular momentum, one of nature's most fundamental and unbreakable principles, determined how fast our planet would spin. Picture, if you will, a figure skater drawing their arms close to their body, spinning faster as they become more compact. Our Earth, gathering itself from a vast cloud of material into a dense sphere, followed this same principle, resulting in this remarkably swift rotation. But let us pause here and truly contemplate what this means. Angular momentum is not just a dry scientific concept, but a profound truth about how the universe organizes itself. Every particle of dust that came together to form Earth brought with it a tiny amount of rotational energy. As these particles drew closer together, pulled by their mutual gravitational attraction, that rotational energy had to be preserved. It couldn't disappear, couldn't be destroyed, it could only be transformed. And so, as the Earth became smaller and denser, it spun faster, like a cosmic whirlpool drawing itself tight. This process wasn't violent or chaotic. It was a gentle gathering, taking millions of years, each particle finding its place in the growing sphere that would become our home. The dust and gas that formed Earth came from the same nebula that birthed our sun, material that had been floating in space for perhaps billions of years before that. Material that itself came from earlier generations of stars that had lived and died long before our solar system was even a possibility. In this way, the rapid rotation of early Earth was inherited from the rotation of that ancient nebula, which inherited its rotation from the galaxy itself, creating a chain of angular momentum that connects our planet to the largest structures in the universe. The story of Earth's changing day is fundamentally a tale of cosmic companionship, a billions-year dance between our planet and its faithful companion, the Moon. But the Moon itself has a remarkable origin story that directly relates to Earth's rotation. According to the most widely accepted theory, the Moon was born from a tremendous collision between the young Earth and a Mars-sized body called Theia. This collision, sometimes called the Big Splash or the Giant Impact, happened perhaps 30 to 50 million years after Earth began forming. Imagine this cosmic collision not as a destructive catastrophe, but as a creative event, a moment of transformation that would define the Earth-Moon system for billions of years to come. When Theia struck Earth, it hit at an angle, not head-on, but glancing, like a cosmic billiard ball transferring its momentum. This impact did several remarkable things at once. It tilted Earth's axis, giving us the seasons we know today. It blasted enormous amounts of material into orbit around Earth, material that would gradually coalesce to form the Moon. And it affected Earth's rotation, possibly speeding it up even more, contributing to those incredibly brief days of the early Earth. The material thrown into orbit by this impact was initially a ring of hot, molten rock and vapor surrounding Earth. Not unlike the rings we see around Saturn today, but hot and glowing rather than cold and icy. Over time, perhaps just a few years or decades, this material began to clump together, drawn by gravity into larger and larger pieces, eventually forming the Moon. But here's the remarkable thing. The Moon formed very close to Earth, perhaps only 15,000 miles away, compared to today's comfortable distance of nearly 240,000 miles. This proximity created a gravitational embrace so intimate that it fundamentally shaped both worlds in ways that still influence us today. The newly formed Moon, still hot and molten from its violent birth, would have appeared enormous in Earth's sky. If there had been observers, they would have seen a glowing orb perhaps 16 times larger in apparent size than the Moon appears today, dominating the sky, casting shadows even at night, creating a perpetual twilight when it was above the horizon. Picture the ancient Earth spinning like a gentle top, turning with youthful grace beneath this enormous Moon. The gravitational interaction between these two bodies was intense, immediate, and would set in motion processes that continue to this day. The Moon, through the soft pull of gravity, began immediately to slow Earth's spin through what scientists call tidal friction. This isn't a forceful restraint, but rather a soft, persistent influence, like honey slowly pouring from a jar on a warm afternoon, or like a feather falling through thick, still air, gradually finding its peaceful descent. To understand tidal friction, we need to appreciate that gravity doesn't just pull on objects as a whole, but creates what physicists call a gradient, a difference in gravitational force from one side of an object to the other. The side of Earth facing the Moon experiences slightly stronger gravitational pull than the center of Earth, which in turn experiences stronger pull than the far side. This differential creates a stretching effect, causing Earth to bulge slightly toward the Moon. But here's where it becomes interesting and beautiful. Earth is rotating beneath these bulges faster than the Moon is orbiting. Imagine Earth spinning rapidly while the tidal bulges try to stay aligned with the Moon. The rotation carries the bulges slightly ahead of the Moon's position. This misalignment means the bulges are pulling the Moon forward in its orbit, while the Moon is pulling the bulges backward against Earth's rotation. It's a cosmic tug-of-war that has been going on for billions of years, with profound consequences for both bodies. The solid Earth, though it seems rigid to us, actually flexes like a massive ball of warm clay, rising and falling by several feet as the Moon passes overhead. The oceans, of course, respond even more dramatically. This flexing, this gentle breathing of our planet, gradually dissipates rotational energy as heat so minimal that it could never be felt, infinitesimal amounts of warmth that radiate away into space. But accumulated over billions of years, this energy loss has transformed the very nature of time on our world. In those ancient days, with the Moon so close and Earth spinning so fast, the tides would have been magnificent beyond current imagination. Yet they moved with a peaceful inevitability. With the Moon so close, water would have risen and fallen in tremendous but gentle sweeps across the protocontinents. These weren't violent or destructive movements, but rather like the slow breathing of a sleeping giant, rhythmic and constant. The water would advance and retreat, perhaps 8 times in what we would now call a single day. Each tide lasting less than an hour, creating a world of constant but gentle change. But we must remember that in those earliest days, there might not have been liquid water oceans as we know them. The Earth was still very hot, and the atmosphere was thick with steam and other gases. The first oceans may have been more like a dense, hot fog that enveloped the entire planet, gradually condensing as the surface cooled. When liquid oceans finally did form, they would have been hot, perhaps near boiling, filled with dissolved minerals from the newly formed rocks, nothing like the cool blue waters we know today. Let us paint a peaceful picture of this ancient world, this Earth of 6-hour days. The period scientists call the Hadean Eon, named not for any hellish conditions, but for the profound transformations occurring, was actually a time of unique beauty and strange tranquility when viewed from the proper perspective. The sky, had there been observers, would have appeared in soft shades of orange and amber, filled with a thick atmosphere rich in methane, ammonia, carbon dioxide, and water vapor, creating perpetual sunset colors even at what would have been noon. There was no harsh blue sky, no glaring sun, but rather a warm, diffused light that bathed everything in gentle golden hues. The atmosphere itself was perhaps hundreds of times denser than today's, creating a massive greenhouse effect that kept the surface warm despite the sun being about 30% dimmer than it is now. This thick atmosphere would have created enormous pressure at the surface, perhaps similar to being dozens of meters underwater today. Sound would have traveled differently in this dense air, and the wind, when it blew, would have had a different quality, more like a thick, warm current than the breezes we know. The surface of our young planet was a constantly shifting canvas of creation, but not in any violent sense. Volcanic activity wasn't disruption, but rather Earth's way of breathing, releasing heat and gases in a continuous, gentle exhale that would last for millions of years. Picture not explosive eruptions, but rather countless spots where the Earth quietly seeped lava like warm honey, building layer upon layer of new rock in patient accumulation. These weren't the tall volcanic cones we see today, but rather vast, flat flows of basaltic lava, spreading like syrup across the ancient surface, creating the first solid ground. These volcanic expressions were essential for the development of our world. They brought gases from Earth's interior to the surface, gradually building the atmosphere. They brought water vapor that had been locked in the rocks, contributing to the eventual formation of oceans. They brought minerals and nutrients that would, billions of years later, become essential for life. Every volcano was like a gentle fountain, bringing gifts from the deep earth to the surface, participating in the great circulation that would eventually make our planet habitable. The landscape of this early Earth would have been unlike anything in our current experience, yet strangely peaceful in its own way. There were no plants to soften the harsh geology, no soil as we know it, just endless vistas of dark volcanic rock, still warm to the touch, occasionally pooled with water that had begun to condense from the cooling atmosphere. The horizons would have seemed closer due to the lack of vegetation to provide scale, creating an intimate, enclosed feeling, like being in a vast, quiet room. The rocks themselves would have been different from most rocks we see today. These were primary rocks, formed directly from cooling magma, without the complex history of weathering, erosion, and reformation that characterizes most of Earth's current surface. They were pristine in a way, unmarked by life, unweathered by oxygen, unchanged by the billions of years of geological processes that would follow. These rocks were mostly dark basalt, similar to what we see in Hawaii or Iceland today, but covering the entire planet. Between the volcanic flows, pools of water would have collected, the first puddles that would eventually become oceans. These pools would have been strange by our standards, filled with dissolved minerals, perhaps colored green or brown by iron compounds, warm from the heat of the rocks, and constantly evaporating and reforming as the temperature fluctuated. They would have been acidic, filled with dissolved carbon dioxide and sulfur compounds from the volcanic gases, creating a chemistry very different from modern seawater. In this 6-hour day world, the pace of everything was different, yet remarkably stable. The rapid succession of day and night meant that temperatures couldn't vary as dramatically as they do now. Each brief day brought a quick, gentle warming. Each brief night, a mild cooling, creating a more uniform temperature across the planet's surface. This thermal stability would have been enhanced by the thick atmosphere, which would have acted like a blanket, trapping heat and moderating temperature changes. Think about what this means for the development of the planet. On modern Earth, the day-night temperature difference can be extreme, especially in deserts where it might be scorching hot during the day and near freezing at night. But on early Earth, with its 6-hour days and thick atmosphere, these extremes couldn't develop. The brief nights didn't last long enough for significant cooling, and the brief days didn't last long enough for extreme heating. This created a more homogeneous environment, where conditions were similar across much of the planet's surface. The winds of this ancient Earth would have been unlike anything in our current experience, yet they moved with a peculiar grace. With such rapid rotation, the Coriolis effect, that gentle force that curves the path of moving air, would have been much stronger. This force, which barely affects small-scale movements on modern Earth, would have been noticeable even in relatively small weather systems on the rapidly spinning early Earth. Weather patterns would have been tighter, more compact, creating swirling patterns of clouds that spiraled in intricate, mesmerizing designs across the sky. These weren't violent storms, but rather like watching cream swirl into coffee. Constant motion, but gentle, hypnotic, peaceful. The rapid rotation would have created numerous small circulation cells rather than the large Hadley cells we see today. Imagine the atmosphere divided into many small compartments, each with its own circulation pattern, like a honeycomb of weather systems covering the planet. Storms, when they formed, would have been different in character. They would have been smaller in diameter, but possibly more numerous. The rapid rotation would have given them a tight spiral structure, like miniature hurricanes, but without the extreme violence we associate with modern tropical cyclones. These storms would have formed and dissipated quickly, their life cycles measured in hours rather than days, constantly reforming and dissolving in the thick, warm atmosphere. The rain, when it fell in this early world, would have been warm and gentle, like a tropical shower that never ends. But this rain was not the pure water we know today. It was acidic, filled with dissolved gases from the atmosphere, particularly carbon dioxide and sulfur compounds. This acid rain was actually beneficial for the young Earth, as it helped to weather the rocks, breaking them down and beginning the long process of soil formation. Every raindrop was a tiny chemical factory, reacting with the rocks, dissolving minerals, and carrying them to the growing oceans. The water cycle was just beginning to establish itself, and it operated differently than today. Water vapor rising from the warm oceans would quickly condense in the cooler upper atmosphere, but with the rapid rotation, it wouldn't travel far before falling back as rain. This created a more localized water cycle, with water evaporating and falling in the same general area, rather than being transported thousands of miles, as happens today. Lightning would have been common in this early atmosphere, perhaps more common than today. The thick atmosphere, filled with volcanic gases and water vapor, would have been ideal for generating electrical charges. But imagine this lightning not as frightening bolts, but as a constant, gentle flickering, like a candle flame dancing in the thick air. This lightning was important, as it provided energy for chemical reactions in the atmosphere, possibly creating some of the first organic molecules that would eventually lead to life. As we contemplate this ancient Earth, we find echoes of its reality in the myths and wisdom of cultures throughout human history. Though no human eyes witness these 6-hour days, something deep in our collective consciousness seems to remember that time itself has not always moved at the pace we know. These mythological memories, passed down through countless generations, might preserve some deep truth about the nature of our world and our place in it. Ancient Hindu cosmology speaks of different yugas, or ages, where time moves differently, where the very fabric of existence operates according to different rules. The Satya Yuga, the age of truth and perfection, is described as lasting 1,728,000 years. But these are not ordinary years. In this age, a day of the gods was said to be equal to a year of mortals, suggesting an understanding that time itself can have different qualities, different densities. The Hindu sages spoke of cosmic cycles within cycles, wheels of time turning at different rates, a vision that resonates remarkably with our modern understanding of the varying day lengths throughout Earth's history. The Vedic texts describe the beginning of creation as emerging from a golden egg, the Hiranyagarbha, floating in a void for a year before hatching. But this was not an ordinary year. It was a year without days or nights as we know them, a year outside of normal time. This mythological description parallels in a poetic way our scientific understanding of Earth's formation from a nebula, a process that occurred before the establishment of the day-night cycle we know. The Aboriginal Australians, whose oral traditions stretch back perhaps 60,000 years, making them among the oldest continuous cultural traditions on Earth, speak of the dream time, an era when the world was soft and malleable, still being shaped by the movements of ancestral beings. In the dream time, the normal rules of space and time didn't apply. Ancestors could travel vast distances instantly, mountains could be formed in moments, and the landscape was fluid and changeable. This mythological time, before the world hardened into its current form, resonates remarkably with our scientific understanding of Earth's early, more plastic state. The Dreamtime stories speak of a gradual solidification, a hardening of the world into its current form, much as Earth actually did cool and solidify over millions of years. The Aboriginal peoples speak of this, not as a time that ended, but as a time that continues to exist parallel to our ordinary time, accessible through dreams and ceremony, suggesting an intuitive understanding that different temporal realities can coexist. The rainbow serpent, a central figure in many Aboriginal traditions, is described as shaping the landscape, carving out rivers and valleys with its movement. This serpent is often associated with water, with the cycle of seasons, and with the creation of celestial bodies. The undulating movement of the rainbow serpent through the landscape could be seen as a metaphor for the tidal forces that have shaped Earth over billions of years, the same forces that have gradually slowed our planet's rotation. Norse mythology tells of the primordial realm of Ginnungagap, a vast, peaceful emptiness where fire and ice met to create the world. This void existed before the creation of the Earth, before time as we know it began. From the meeting of fire from Muspelheim and ice from Niflheim, the first beings emerged, and eventually the world was formed from their bodies. This poetic description mirrors, in its own way, the scientific narrative of Earth's formation from the collision and coalescence of cosmic materials, hot and cold, coming together in the void of space. The Norse also spoke of different worlds existing simultaneously, connected by the world tree Yggdrasil. Each world had its own nature, its own rules, perhaps even its own flow of time. Asgard, the realm of the gods, operated on a different temporal scale than Midgard, the realm of humans. This multi-layered cosmos, with different realms operating according to different principles, suggests an understanding that reality is not monolithic, that different states of existence can coexist. In Norse cosmology, the end of the world, Ragnarok, is not truly an end, but a transformation, after which a new world will emerge, green and fresh, from the waters. This cycle of destruction and renewal, of worlds ending and beginning, parallels the geological understanding of Earth's constant transformation, its surface constantly being renewed through volcanic activity and erosion, its rotation constantly changing through tidal friction. Chinese mythology speaks of Pangu, the primordial being who separated heaven and earth, standing between them as they slowly moved apart over eons. For 18,000 years, Pangu grew taller each day, pushing the sky higher and the earth lower, until finally, exhausted, he lay down and his body became the features of the world. His breath became the wind, his voice the thunder, his left eye the sun, and his right eye the moon. This image of gradual separation and the establishment of cosmic order parallels our understanding of how Earth's rotation has gradually slowed, how the moon has gradually retreated, how the cosmic dance has evolved over billions of years. Pangu's growth of 10 feet per day for 18,000 years suggests a patient, gradual process of world formation, not unlike the slow processes that have actually shaped our planet. The Chinese concept of qi, the fundamental energy that flows through all things, changing but never being destroyed, mirrors the scientific principle of conservation of energy that governs Earth's rotational evolution. As Earth's rotational energy decreases, it doesn't disappear, but transforms into the moon's orbital energy, just as qi transforms but never vanishes. Ancient Egyptian mythology describes the time before creation as the waters of Nun, an infinite, dark, watery abyss that existed before the world. From these waters emerged the first land, the primordial mound, upon which the god Atum stood to begin creation. This emergence from primordial waters mirrors Earth's early history, when the first solid land emerged from a world covered in hot, shallow seas. The Egyptians also had a sophisticated understanding of time cycles. They recognized different qualities of time. Nehe, the time of cycles and repetition, and Jet, the time of completion and permanence. This dual nature of time, both cyclical and linear, reflects the actual nature of Earth's rotation, which is both cyclical in its daily repetition and linear in its gradual slowing. The Egyptian god Khepri, often depicted as a scarab beetle pushing the sun across the sky, represented the morning sun and the concept of coming into being. The image of the scarab rolling its ball of dung, in which it lays its eggs, became a symbol for the sun's journey across the sky. But this journey was not seen as always having been the same. Egyptian texts speak of times when the cosmic order was different, when the gods walked the earth, when the very nature of existence was different from what humans experience. Greek mythology tells of the Titans, the old gods who ruled before the Olympians, representing an earlier state of the cosmos. Kronos, the Titan of time, devoured his own children, only to be overthrown by Zeus, establishing a new order. This succession of cosmic orders, each with its own rules and nature, parallels the scientific understanding of Earth's evolution through different states, each with its own characteristic day length and conditions. The Greeks also had Kronos, distinct from Kronos, a primordial deity representing time in its most fundamental aspect. Kronos was described as serpentine, wrapped around the cosmic egg from which the ordered universe emerged. This image of time as something that constrains and shapes the cosmos resonates with how Earth's rotation, our most basic measure of time, has been shaped by cosmic forces over billions of years. The Orphic cosmogony speaks of a cosmic egg that existed before the creation of the world, floating in the void for countless ages before hatching to reveal Phanes, the god of creation. This egg was sometimes described as silver, like the moon, and its hatching brought forth not just the world, but time itself. The pre-existence of the egg before time began suggests an understanding that there are states of existence outside our normal temporal experience. In Mesopotamian mythology, the Enuma Elish describes the creation of the world from the mingling of two primordial waters, Apsu, the fresh water, and Tiamat, the salt water. Their mingling created the gods, who eventually ordered the cosmos. But before this ordering, there was a state of fluid chaos, where the boundaries between things were not fixed, where time and space were not yet separated into their current forms. The Babylonians had a sophisticated understanding of astronomical cycles, tracking the movements of planets and stars over long periods. They recognized that these cycles were not perfect, that there were gradual changes over time. Their observations of the precession of the equinoxes showed them that even the seemingly eternal heavens were slowly changing, that time itself had a deeper structure than the simple cycle of days and years. Japanese mythology speaks of the age of the gods, a time before human history when divine beings shaped the world. In this age, time moved differently. The gods could accomplish in moments what would take humans years. The sun goddess Amaterasu could hide in a cave and plunge the world into darkness, only to emerge and restore light, suggesting a time when the cycle of day and night was not yet fixed and regular. The Shinto concept of musubi, the interconnecting energy that binds all things, resembles the gravitational forces that bind Earth and Moon, slowly transferring energy between them. This binding force is not static, but dynamic, constantly creating new connections and relationships, just as the Earth-Moon system continues to evolve. Native American traditions often speak of a time when the world was different, when animals could speak, when the boundaries between waking and dreaming were fluid. The Hopi speak of previous worlds that existed before this one, each destroyed and remade, each with its own characteristics. We are now in the fourth world, they say, and there will be a fifth world to come. These successive worlds are not just replacements, but evolutionary stages, each building on what came before. The first world was a pure state, close to the Creator, but it became corrupted and had to be destroyed. Each subsequent world has been further from that original perfection, but has also developed new qualities, new possibilities. This vision of cosmic evolution through discrete stages parallels the geological understanding of Earth's evolution through different eons, each with its own characteristic conditions. The Lakota tradition speaks of Maka, the Earth, as a living being who has gone through many changes. In the beginning, Maka was soft and without features, but through various trials and transformations, she became the Earth we know. This transformation was not sudden, but gradual, involving many spirits and forces working over vast periods of time. The transformation from 6-hour days to our current 24-hour cycle represents one of the most patient processes in nature, a process so slow that it challenges our very ability to comprehend time. Each century, Earth's day grows longer by approximately 1.7 milliseconds. To put this in perspective, this is less than the time it takes for a hummingbird to complete a single wing beat. This change is so gradual, so gentle, that if you could live for 1,000,000 years, you would notice the day had grown longer by only about 17 seconds. Let us think about this rate of change in different ways to truly appreciate its subtlety. If you were to watch a tree grow from a seedling to maturity, you would observe a change roughly 1 billion times faster than the slowing of Earth's rotation. The movement of continents, which we think of as impossibly slow, with North America and Europe separating at about 2 centimeters per year, is more than 10 million times faster than the rate at which our days are lengthening. Even the evolution of species, which we think of as occurring over vast timescales, happens at a pace that makes Earth's rotational slowing seem almost frozen. The evolution of humans from our ape-like ancestors took perhaps 7 million years. In that time, Earth's day has lengthened by only about 12 seconds. The entire rise and fall of the dinosaurs, spanning more than 150 million years, saw the day grow longer by only about 4 minutes. This slowing follows beautiful mathematical principles that govern the universe itself. The angular momentum of the Earth-Moon system remains constant, like a cosmic law written into the fabric of space-time itself. This conservation law is one of the most fundamental principles in physics, arising from the very symmetry of space itself. Because the laws of physics are the same regardless of which direction you're facing, angular momentum must be conserved. This deep connection between symmetry and conservation laws was one of the most profound discoveries in 20th century physics. As Earth slows its spin, that rotational energy doesn't disappear into nothingness. According to the conservation of energy, another fundamental law, energy can neither be created nor destroyed, only transformed from one form to another. The rotational energy Earth loses is transferred to the Moon, pushing our companion farther away at a rate of about 3.8 centimeters per year. This is roughly the same speed at which your fingernails grow, or the rate at which the Atlantic Ocean is widening due to seafloor spreading. Imagine this as a cosmic conservation principle, where nothing is truly lost, only gently transformed. The energy of Earth's youthful spin has been gradually gifted to the Moon, lifting it higher in its orbit. But this isn't a simple linear exchange. As the Moon moves farther away, its gravitational influence on Earth weakens, which means the rate of tidal friction decreases. This creates a negative feedback loop, a self-regulating system that ensures the process becomes ever more gradual over time. The mathematics of this orbital evolution follow Kepler's laws, discovered 4 centuries ago by Johannes Kepler as he studied the motion of planets. As the Moon's orbit expands, its orbital period also increases, following a precise mathematical relationship. The square of the orbital period is proportional to the cube of the orbital radius. This means that as the Moon slowly spirals outward, not only does it take longer to complete each orbit, but the rate of increase accelerates according to this power law. Currently, the Moon takes about 27.3 days to orbit Earth. When it was at its closest, perhaps 15,000 miles away, it would have completed an orbit in just a few days. In the far future, when the Earth and Moon become tidally locked, the Moon's orbital period will match Earth's rotational period, both lasting perhaps 47 of our current days. This represents the end point of the process, a state of equilibrium that the system is slowly approaching. But let's delve deeper into the mechanism of tidal friction itself. To truly understand this cosmic engine that has been running for billions of years, the tidal bulges that the Moon raises on Earth are not perfectly aligned with the Moon's position. Because Earth rotates faster than the Moon orbits, friction carries these bulges slightly ahead of the Moon. For the ocean tides, this offset is typically about 3 degrees. For the solid Earth tides, the offset is smaller, but still present. This misalignment means that the gravitational pull between the tidal bulges and the Moon is not perfectly radial. There's a component of the force that acts tangentially to the moon's orbit, accelerating it forward. By Newton's third law, there's an equal and opposite force acting on the bulges, slowing Earth's rotation. It's like two dancers holding hands and spinning. If one slows down, the other must speed up to conserve the total angular momentum of the system. The amount of energy dissipated through tidal friction is enormous by human standards, but tiny compared to Earth's total rotational energy. Currently, about 3.7 terawatts of power are dissipated through tidal friction. That's about twice the total power consumption of human civilization. Yet Earth's rotational energy is so vast that this loss rate only lengthens the day by milliseconds per century. Most of this energy dissipation occurs in shallow seas, where tidal currents are forced through narrow straits and around complex coastlines. The English Channel, the Irish Sea, the Bering Strait. These are the places where Earth's rotation is most effectively converted into heat through turbulent water motion. In the deep oceans, tidal dissipation is much less efficient, as the water can move more freely without generating as much friction. The solid Earth also experiences tidal dissipation, though less than the oceans. As the solid Earth flexes under the moon's gravitational pull, internal friction converts some of the deformation energy into heat. This process is most effective in Earth's mantle, where the hot rock can flow over long time scales but resists rapid deformation. The efficiency of this solid Earth tide dissipation depends on the internal structure of our planet, particularly the viscosity of the mantle. When life first emerged on Earth, perhaps 3.8 billion years ago, it entered a world where days were considerably shorter than our own. By this time, Earth's rotation had already slowed significantly from those initial 6-hour days. Days might have lasted perhaps 12 hours, still brief by our standards, but long enough for the planet to have cooled, for oceans to have formed, for the first chemical experiments that would lead to life. These early life forms were simple, single-celled organisms, probably similar to modern bacteria or archaea. They had no eyes to see the rapid sunrises and sunsets, no nervous systems to experience the passage of time. Yet they were profoundly influenced by the rhythm of their world. The fundamental biochemical processes that they developed had to function in harmony with these 12-hour days. Consider how different photosynthesis might have developed in a world of shorter days. Photosynthesis, the process by which organisms convert sunlight into chemical energy, is one of the most important innovations in the history of life. It not only provides energy for most of Earth's biosphere, but also produced the oxygen that transformed our atmosphere. The cyanobacteria, those ancient architects of our oxygen atmosphere, evolved their photosynthetic machinery in a world of shorter days. These organisms would have had to be remarkably efficient, capturing sunlight in 6-hour windows before darkness returned. But this wasn't a disadvantage. It was simply the environment they evolved in. Their photosynthetic apparatus became optimized for rapid response to changing light conditions. Even today, we can see this legacy in how quickly photosynthetic organisms can adjust to changes in light intensity. The circadian rhythms that govern all life on Earth would have been tuned to these different day lengths. Circadian rhythms are internal biological clocks that help organisms anticipate and prepare for regular environmental changes. Almost all organisms, from bacteria to humans, have these internal timekeepers. They regulate everything from gene expression to behavior, from cell division to sleep cycles. These biological clocks are remarkably flexible, able to adjust to different day lengths within certain limits. This flexibility might be a legacy from Earth's history of changing day lengths. As days gradually lengthened over geological time, life had to continuously adjust its internal rhythms. Organisms that couldn't adapt would have been at a disadvantage, while those with flexible circadian systems thrived. Even now, in our genetic code, we might carry echoes of these ancient timekeepers. Studies of circadian genes show that they're highly conserved across different species, suggesting they evolved very early in the history of life. The basic molecular machinery of biological clocks, involving feedback loops of gene expression and protein production, might have been established when days were much shorter than they are now. In the shallow seas of the ancient Earth, where most early life congregated, the rapid tidal cycles created by the nearby moon would have been a dominant force shaping evolution. Imagine tidal pools that filled and emptied not twice a day as now, but perhaps 8 times in what we would call a single day. Life in these pools would have experienced rapid cycles of immersion and exposure, forcing rapid adaptations to changing conditions. These frequent tidal cycles might have actually accelerated evolution in these environments. Each tide brought new nutrients, removed waste products, and mixed populations of organisms. The constant environmental variation would have selected for versatility and resilience. Organisms that could quickly switch between different metabolic states, that could survive both aquatic and semi-terrestrial conditions, would have thrived. The stromatolites, those ancient structures built by cyanobacteria that we can still see fossilized today, grew in these conditions. These layered structures, looking like rocky cushions or domes, are among the earliest evidence of life we have. Each layer in a stromatolite represents a growth period, possibly corresponding to ancient daily or tidal cycles. When we look at these fossils, we're looking at a record of time itself, preserved in stone. The layers in ancient stromatolites are typically much thinner than those in modern stromatolites, suggesting they were deposited more frequently. This matches what we would expect if days were shorter and tidal cycles more frequent. By carefully analyzing these layers, scientists have been able to estimate day lengths at different points in Earth's history, turning these humble bacterial mats into cosmic chronometers. But stromatolites weren't just passive recorders of time. They were active participants in Earth's evolution. Through photosynthesis, they gradually increased the oxygen content of Earth's atmosphere, fundamentally changing the chemistry of our planet. This oxygenation event, sometimes called the Great Oxidation Event or the Oxygen Catastrophe, occurred about 2.4 billion years ago and represents one of the most significant changes in Earth's history. The timing of this event might not be coincidental. By 2.4 billion years ago, days had lengthened to perhaps 18 hours. This meant that photosynthetic organisms had longer periods of continuous sunlight to produce oxygen. The longer days might have tipped the balance, allowing oxygen production to finally exceed oxygen consumption by geological and chemical processes. As we move forward through geological time, we can trace the gradual lengthening of days through various geological and fossil markers. The evidence is written in stones, in the growth patterns of ancient organisms, in the sediment layers deposited by ancient tides. Each piece of evidence tells us something about the length of days at a particular point in Earth's history. Coral fossils have proven particularly valuable for this purpose. Corals, like trees, show growth rings, but they have both daily and annual patterns. Modern corals show about 365 fine growth lines per year, corresponding to daily growth variations. But fossil corals from the Devonian period, about 400 million years ago, show about 400 fine lines per year, indicating that years had more days because each day was shorter. By counting these growth lines in corals of different ages, scientists have been able to track the gradual lengthening of Earth's day through hundreds of millions of years. The data shows a remarkably consistent trend. Days have been lengthening at an average rate of about 2 milliseconds per century over the past few hundred million years, though the rate has varied depending on factors like the arrangement of continents and the extent of shallow seas. Bivalve shells also preserve records of ancient day lengths. Like corals, many bivalves show daily and seasonal growth patterns. Some species that live in tidal zones show additional patterns corresponding to tidal cycles. By analyzing these patterns in fossil shells, scientists can determine not just day length, but also the frequency and intensity of ancient tides. Even sedimentary rocks can preserve information about ancient day lengths. Tidal rhythmites are finely layered sedimentary rocks formed in ancient tidal environments. Each layer represents a single tidal cycle, and bundles of layers correspond to longer cycles, like the spring-neap tide cycle, caused by the alignment of the sun and moon. By counting and analyzing these layers, geologists can reconstruct the tidal patterns of ancient seas and, from those, calculate the day length and lunar distance. One particularly spectacular example of tidal rhythmites comes from the Big Cottonwood Formation in Utah, dating to about 900 million years ago. These rocks show clear evidence of tidal cycles, with layer patterns indicating that days were about 18 hours long at that time. The rocks also preserve evidence of the lunar month, which was then about 20 days long compared to the current 29.5 days. The lengthening of days hasn't been perfectly uniform throughout Earth's history. There have been periods when the rate of slowing increased or decreased, depending on various factors. The arrangement of continents affects tidal dissipation, with certain configurations creating more shallow seas where tidal friction is most effective. Ice ages also affect the process, as ice sheets lock up water that would otherwise contribute to tidal friction. During the late Proterozoic, about 600 to 800 million years ago, there's evidence that day length remained relatively stable or even shortened slightly. This period, sometimes called the Boring Billion, because of its apparent geological stability, might have experienced unusual tidal dynamics due to the configuration of continents. Some scientists suggest that the continents were arranged in a way that minimized tidal dissipation, temporarily halting or even reversing the usual trend of rotational slowing. The breakup of supercontinents appears to accelerate rotational slowing by creating more shallow seas and complex coastlines where tidal energy can be dissipated. When Pangaea broke apart beginning about 200 million years ago, it likely increased the rate of tidal friction. The opening of the Atlantic Ocean created new sites for tidal dissipation, particularly in the shallow seas around Europe and North America. Let us dream for a moment of alternative Earths, peaceful worlds where different cosmic circumstances led to different outcomes. These aren't just flights of fancy, but thought experiments that help us understand how special our Earth-Moon system is and how different life might be under different conditions. Imagine if Earth had formed without a moon, or with a moon so small its gravitational influence was negligible. Without significant tidal friction, Earth might still be spinning much faster today. Perhaps we would have 16-hour days, with 8 hours of daylight and 8 hours of night. The weather patterns would be completely different, dominated by the stronger Coriolis effect of the faster rotation. In this moonless world, the weather would be dominated by smaller, more numerous storm systems. The jet streams would be stronger and located closer to the equator. Hurricanes, if they formed at all, would be smaller and more frequent, spinning up quickly in the rapid rotation. The lack of lunar tides would mean coastal environments would be very different, without the intertidal zones that have been so important for the evolution of life on our Earth. The absence of lunar tides would also affect the ocean circulation. On our Earth, tides help mix the ocean waters, bringing nutrients from the deep to the surface and helping regulate global temperature. Without this mixing, the oceans might be more stratified, with less exchange between surface and deep waters. This could lead to very different patterns of marine productivity and climate. Without the moon's stabilizing influence on Earth's axial tilt, the climate would be much more chaotic. Earth's axis would wobble dramatically over time, potentially tilting as much as 85 degrees. This would create extreme seasonal variations, with the poles sometimes pointing almost directly at the sun. Such dramatic climate swings would make the evolution of complex life much more challenging. Or consider an Earth with a larger moon, perhaps twice the mass of our current moon. Such a moon would have exerted much stronger tidal forces, slowing Earth's rotation more rapidly. We might now have 36 or even 48-hour days. The longer days would create extreme temperature differences between day and night, with scorching days and freezing nights in many regions. Life on such a world would need different strategies to cope with the extended periods of light and darkness. Plants might have evolved more efficient energy storage systems to survive the long nights. Animals might have evolved migration patterns, constantly moving to stay in the twilight zones. Or perhaps life would be concentrated in the polar regions, where the sun would trace long, low circles around the horizon, providing more consistent illumination. The stronger tidal forces of a larger moon would create massive tides, perhaps hundreds of feet high. Coastal regions would be uninhabitable by terrestrial life, constantly swept by enormous walls of water. Life might be restricted to highland areas, or perhaps marine life would dominate, with only a few species adapted to the extreme intertidal zones. Imagine an Earth with multiple moons, each contributing its own tidal influence. The tides would create complex interference patterns, sometimes reinforcing each other to create supertides, sometimes canceling out to create periods of calm. The night sky would be a constantly changing tableau of moons in different phases, creating complex patterns of light and shadow. Life would need to adapt to these complex tidal patterns. Perhaps organisms would evolve sophisticated internal calendars to predict the tidal cycles. Breeding and feeding might be timed to coincide with particular tidal configurations. The complex gravitational environment might even affect the evolution of sensory systems, with organisms developing the ability to sense gravitational gradients. The interaction between multiple moons would make their orbits unstable over long timescales. Moons might occasionally collide or be ejected from orbit, causing catastrophic changes to Earth's environment. This instability might reset evolution periodically, preventing the development of very complex ecosystems. Or perhaps life would evolve to be extremely resilient, able to survive and rapidly recover from such catastrophes. Consider a binary planet system, where Earth had a companion of similar size rather than a small moon. The two planets would orbit their common center of mass, probably tidally locked to each other, so the same faces always pointed toward each other. Days would be as long as the orbital period, perhaps weeks or months. On such a world, one hemisphere would always face the companion planet, experiencing regular eclipses as the companion passed in front of the sun. The other hemisphere would never see the companion, having a clear view of the stars. The two hemispheres might develop completely different ecosystems adapted to their different sky conditions. Or imagine an Earth in a different orbit, closer to or farther from the sun. The length of the year would be different, changing the relationship between days and years. Closer to the sun with a shorter year, there might be fewer days per year, changing the seasonal patterns. Farther out, with a longer year, there would be more days per year, perhaps allowing for more complex seasonal cycles. These alternative Earths aren't just fantasies. They likely exist somewhere in the vast cosmos. Among the thousands of exoplanets we've discovered, there are surely worlds with every conceivable day length. Some are tidally locked to their stars, with permanent day and night sides. Others spin so fast, their days last just a few hours. Each represents a different solution to the problem of being a planet, a different way of existing in the universe. Hot Jupiters. Massive planets orbiting very close to their stars are often tidally locked, with permanent day and night hemispheres. The day side might reach temperatures of thousands of degrees, while the night side could be cold enough for some gases to condense. Powerful winds would transport heat from day to night, creating a dynamic atmosphere unlike anything in our solar system. Super-Earths, planets larger than Earth but smaller than Neptune, might have retained more of their primordial rotation, spinning rapidly with days lasting just a few hours. Their strong gravity would allow them to hold onto thick atmospheres despite the rapid rotation. Weather patterns would be dominated by numerous small cells, creating a banded appearance like Jupiter. Planets around red dwarf stars, the most common type of star in the universe, face unique challenges. To be warm enough for liquid water, they must orbit very close to their dim stars. At such close distances, tidal forces quickly slow their rotation, often leading to tidal locking. Life on such worlds, if it exists, must cope with permanent day and night, perhaps living in the twilight zone between the two extremes. Some planets might have retrograde rotation, spinning backwards compared to their orbital motion. Venus in our own solar system is an example, with its day longer than its year. The causes of retrograde rotation are still debated, possibly involving massive impacts or gravitational interactions with other planets. Life on such worlds would experience the sun rising in the west and setting in the east, if concepts like east and west even make sense on an alien world. Rogue planets, ejected from their stellar systems and drifting through interstellar space, would have no days at all in the conventional sense. Without a sun to rise and set, they would exist in permanent darkness, perhaps warmed only by internal radioactive decay or residual heat from their formation. If life existed on such worlds, it would need to be independent of sunlight, perhaps clustered around volcanic vents like the deep sea communities on Earth. Looking forward into the deep future, Earth's days will continue to lengthen, though the process will gradually slow as the moon recedes and its influence weakens. This future evolution is not a matter of speculation, but of physical necessity, as inevitable as the sunrise, though infinitely more gradual. In about 600 million years, assuming current rates continue, a day might last about 25 hours. This might seem like a minor change, just one extra hour, but it would have profound implications for life. The longer nights would be cooler, the longer days warmer, creating greater temperature extremes. Weather patterns would adjust to the new rotation rate, with larger, slower-moving storm systems. By this time, the sun will have grown slightly brighter as it ages, increasing Earth's temperature. The combination of a brighter sun and longer days might create very hot conditions during summer days, possibly making some regions uninhabitable. Life might migrate toward the poles or evolve new strategies for dealing with heat stress. Perhaps plants will develop more reflective leaves, or animals will become primarily nocturnal. In a billion years, days might last 27 hours or more. But by this time, Earth will face more serious challenges than just longer days. The brightening sun will have triggered a runaway greenhouse effect, evaporating the oceans and making the surface uninhabitable for life as we know it. The lengthening days will be just one aspect of a fundamentally transformed world. If Earth somehow maintained habitable conditions, the continued lengthening of days would eventually lead to a tidally locked configuration. In perhaps 50 billion years, if the sun remained stable, Earth and Moon would be mutually tidally locked, always showing the same faces to each other. Days and months would be the same length, about 47 of our current days. This tidally locked Earth would be profoundly different from the world we know. One hemisphere would experience a day lasting weeks, followed by an equally long night. The temperature extremes would be enormous, unless moderated by a thick atmosphere or ocean. The moon would hang motionless in the sky for half the planet, never visible from the other half. But this scenario will never come to pass, because the sun will not remain stable for 50 billion years. In about 5 billion years, the sun will exhaust the hydrogen fuel in its core and begin to evolve into a red giant. As it expands, it will engulf Mercury and Venus, and possibly Earth as well. Even if Earth survives, it will be a charred cinder, its oceans and atmosphere long since boiled away. Before the sun becomes a red giant, it will go through a period of increasing brightness. Over the next billion years, the sun's luminosity will increase by about 10%. This might not sound like much, but it's enough to trigger dramatic climate changes. The extra heat will increase the rate of water evaporation, adding more water vapor to the atmosphere. Since water vapor is a greenhouse gas, this will trap more heat, leading to further warming in a positive feedback loop. Eventually, this process will lead to a runaway greenhouse effect, similar to what happened on Venus. The oceans will evaporate entirely, and the water vapor will be broken apart by ultraviolet radiation in the upper atmosphere. The hydrogen will escape to space, and the oxygen will react with surface rocks. Earth will transform from a blue marble to a hot, dry, lifeless world. But let's not dwell on such distant catastrophes. For hundreds of millions of years yet, Earth will remain habitable, and days will continue their patient lengthening. Each geological era will have its own characteristic day length, its own rhythm of light and dark. Life will continue to adapt, as it always has, to the gradually changing conditions. The story of Earth's rotation is also part of the larger story of the solar system's evolution. All the planets have been gradually evolving toward more stable configurations. Orbits that were once elliptical have become more circular. Axial tilts that were once extreme have moderated. The violent chaos of the early solar system has given way to the clockwork regularity we see today. Mercury, the innermost planet, has already reached a stable rotational state. It's locked in a 3-to-2 resonance with its orbit, rotating 3 times for every 2 orbits around the Sun. This unusual configuration, different from simple tidal locking, results from Mercury's eccentric orbit. From Mercury's surface, the Sun would appear to stop and reverse direction in the sky at certain points in the orbit. Venus, our sister planet, has the most unusual rotation in the solar system. It rotates backwards, retrograde, and extremely slowly, taking 243 Earth days to complete one rotation while orbiting the Sun in 225 Earth days. This means a Venusian day is longer than its year. The cause of this bizarre rotation is still debated. Perhaps a massive impact reversed its spin, or gravitational interactions with the Sun and Earth gradually slowed and reversed it. Mars, being smaller than Earth and lacking a large moon, has maintained a rotation rate similar to Earth's. A Martian day, called a sol, lasts about 24 hours and 37 minutes. This similarity to Earth's day length is coincidental, but fortuitous for future human exploration. Our circadian rhythms can relatively easily adapt to the slightly longer Martian day. The gas giants tell their own stories of rotational evolution. Jupiter, massive and distant from any large moons relative to its size, still spins rapidly, completing a rotation in just under 10 hours. This rapid rotation causes Jupiter to bulge significantly at its equator, making it noticeably ablate. The rapid rotation also drives Jupiter's complex atmospheric dynamics, creating the banded structure and storms like the Great Red Spot. Saturn rotates slightly slower than Jupiter, taking about 10.5 hours. Like Jupiter, this rapid rotation creates an equatorial bulge and drives complex atmospheric patterns. Saturn's rotation rate was actually difficult to determine precisely because different latitudes rotate at different rates, a phenomenon called differential rotation common in gas giants. Uranus has perhaps the strangest orientation in the solar system, tilted on its side with an axial tilt of about 98 degrees. This means it essentially rolls along its orbit rather than spinning upright. The cause is unknown, but likely involves a massive collision early in its history. This extreme tilt creates bizarre seasonal patterns, with each pole experiencing 42 years of continuous sunlight, followed by 42 years of darkness. Neptune, the outermost major planet, rotates in about 16 hours, despite being 30 times farther from the Sun than Earth. Neptune has the fastest winds in the solar system, with speeds reaching up to 2,100 kilometers per hour. These supersonic winds move in the opposite direction of the planet's rotation, another mystery of planetary dynamics. Even the dwarf planets have their rotational stories. Pluto and its moon Charon are mutually tidally locked, always showing the same faces to each other as they orbit their common center of mass. From Pluto's surface, Charon would hang motionless in the sky, never rising or setting. This is the configuration Earth and its moon will eventually reach, billions of years in the future. The moons of the solar system show the end states of tidal evolution. Almost all major moons are tidally locked to their parent planets. Io, Europa, Ganymede, and Callisto all show the same face to Jupiter. Titan shows the same face to Saturn. This ubiquity of tidal locking demonstrates that it's the natural end state of gravitational evolution for close celestial pairs. Some moons have more complex rotational states. Hyperion, a small moon of Saturn, tumbles chaotically, its rotation unpredictable from one orbit to the next. This chaos results from its irregular shape and gravitational interactions with other moons. It's a reminder that not all celestial motions settle into regular patterns. Sometimes, chaos persists. This universal tendency toward tidal locking speaks to something profound about the nature of gravity and time. Gravity doesn't just pull objects together, it orchestrates their movements, gradually conducting them toward synchronization. Given enough time, gravity transforms chaotic motion into rhythmic dance, discord into harmony. The process of tidal locking is not unique to our solar system. We've observed tidally locked exoplanets, particularly those orbiting close to red dwarf stars. The TRAPPIST-1 system, with 7 Earth-sized planets orbiting an ultra-cool dwarf star, likely has all its planets tidally locked. Each world would have a permanent day side and night side, with climates radically different from anything in our solar system. These tidally locked worlds challenge our assumptions about habitability. We tend to think of the day-night cycle as essential for life, but perhaps life could adapt to permanent day or night. The terminator zone, the boundary between day and night, might be the most habitable region, with moderate temperatures and permanent twilight. Organisms might migrate along this zone as the planet's orbit carries it around its star. Time, we often think, is constant and universal, a river flowing at a steady rate everywhere in the cosmos. But the story of Earth's changing day reveals that time, at least as we experience it through the cycle of light and dark, is local, contingent, and constantly evolving. Each world has its own temporal rhythm, its own beat in the cosmic symphony. Einstein's relativity revealed that time is not absolute, but depends on motion and gravity. Time passes slightly slower at sea level than on a mountaintop due to the difference in gravitational potential. Satellites in orbit must account for this time dilation to maintain accurate GPS signals. But these are tiny effects compared to the changes in day length over geological time. The gradual slowing of Earth's rotation raises philosophical questions about the nature of time itself. Is a day defined by Earth's rotation or by our experience of it? When Earth's day lasted 6 hours, was time moving faster, or was it simply divided differently? If we could travel back to ancient Earth, would we experience the rapid days as rushed? Or would they feel normal if our biological rhythms adjusted? These questions touch on the difference between physical time and psychological time. Physical time, measured by atomic clocks and celestial motions, proceeds at a steady rate, accounting for relativistic effects. But psychological time, our subjective experience of duration, varies dramatically. An hour spent in pleasant company passes quickly. An hour in a dentist's chair drags on forever. For organisms that evolved on ancient Earth, the rapid day-night cycle would have felt entirely normal. Their biological clocks would have been tuned to that rhythm. If such organisms could somehow experience our 24-hour days, they might feel like time had slowed to a crawl, with interminable periods of light and darkness. The evolution of sleep might have been different on an Earth, with different day lengths. Sleep, that mysterious state where consciousness fades and the body repairs itself, evolved in the context of the day-night cycle. On a world with very short days, organisms might not sleep at all, or might have very brief rest periods. On a world with very long days, organisms might have multiple sleep periods or might estivate during the long, hot days. Circadian rhythms, those internal biological clocks that govern so much of our physiology, would be entirely different on worlds with different day lengths. Studies of humans in isolation from time cues show that our natural circadian rhythm is actually about 25 hours, slightly longer than our current day. This might be an evolutionary memory of longer days in the past, or preparation for longer days in the future. The gradual slowing of Earth's rotation also speaks to the universe's tendency toward equilibrium, toward balance. The early solar system was a place of violent collisions and extreme conditions. Over billions of years, these extremes have moderated. The wild fluctuations have dampened into regular oscillations. Chaos has given way to order, though an order that continues to evolve. This tendency toward equilibrium is seen everywhere in nature. Hot things cool down unless maintained by an energy source. Concentration gradients dissipate through diffusion. Pendulums gradually stop swinging unless driven. The universe seems to prefer balanced, stable states over extreme, unstable ones. But this isn't a boring, static equilibrium. It's a dynamic balance, constantly adjusting to changing conditions. Earth's rotation continues to slow, but the rate changes depending on factors like ice ages, continental positions, and ocean currents. The moon continues to recede, but the rate varies with Earth's rotation rate. It's a complex dance with many partners, each influencing the others. There's something deeply comforting in this cosmic patience. The universe is in no hurry. It has infinite time to explore every possibility, to work out every detail. Changes that seem impossibly slow to us are perfectly normal on cosmic timescales. The universe operates on a schedule that encompasses all possible experiences, all possible evolutions. This patience extends to the development of complexity itself. From the first atoms formed in the Big Bang to the first stars, took hundreds of millions of years. From the first stars to the first rocky planets, billions of years. From the first planets to the first life, perhaps a billion years more. From the first life to complex multicellular organisms, over 3 billion years. Each step took exactly as long as it needed to take. Human civilization, with its few thousand years of history, is just a fleeting moment in this vast temporal landscape. We've existed for perhaps 150,000th of the time that life has existed on Earth. Our entire recorded history spans a period during which Earth's day has lengthened by less than 1/10 of a second. We are mayflies, commenting on the growth of mountains. Yet, in our brief moment, we've developed the ability to perceive and understand these vast timescales. We can look at fossil corals and determine day lengths from hundreds of millions of years ago. We can measure the moon's recession with laser ranging accurate to millimeters. We can model the future evolution of the Earth-Moon system for billions of years to come. This is perhaps consciousness's greatest achievement: to transcend its own temporal limitations and perceive the deeper rhythms of cosmic time. The story of Earth's rotation is also a story about information preservation. The universe has a kind of memory, written not in books or computer files, but in the arrangements of matter and energy. The current distance to the moon remembers Earth's rotational history. The layers in ancient rocks remember the tidal cycles of vanished seas. The DNA of living organisms remembers the adaptations of countless ancestors to changing day lengths. This cosmic memory is not perfect. Information is lost to entropy, erased by geological processes, overwritten by new events, but enough remains for us to piece together the story. We are detectives, reading clues left by a universe that doesn't deliberately hide its history, but doesn't deliberately preserve it either. The evidence is there for those who know how to look. As we continue our contemplation, let's consider how the changing length of days has influenced the development of consciousness itself. Our brains, like all biological systems, are tuned to the rhythms of our environment. The 24-hour day has shaped our sleep cycles, our hormone production, our patterns of activity and rest. We are creatures of the day-night cycle, our very thoughts influenced by the rotation of our planet. But consciousness is more than just biological rhythms. It's the ability to perceive time, to remember the past and imagine the future, to understand that things were once different and will be different again. This temporal awareness might be the defining characteristic of consciousness. We don't just exist in time. We perceive time, think about time, use time as a tool for understanding the world. The evolution of consciousness might have been different on a world with different day lengths. On a rapidly rotating planet, with days lasting just a few hours, would consciousness have evolved to process information faster? Would thoughts flicker quickly like the rapid days? On a slowly rotating world, would consciousness be more leisurely, thoughts unfolding slowly like the long dawns? Or perhaps consciousness, once evolved, adapts to whatever temporal environment it finds itself in. Humans have shown remarkable ability to adjust to different schedules, to stay awake for days or sleep for unusually long periods when necessary. Shift workers adapt to reversed day-night cycles. Submarine crews function without natural light cues. Perhaps consciousness is fundamentally flexible, able to tune itself to different temporal rhythms. Sleep itself remains one of the great mysteries of consciousness. Why do we need to spend a third of our lives unconscious? What happens during those hours of darkness? Dreams, those strange narratives that unfold while we sleep, seem to exist outside normal time. In dreams, past, present, and future mix freely. We can experience hours of dream time and minutes of real time, or vice versa. Some scientists suggest that sleep evolved to conserve energy during the dark hours when our ancestors couldn't safely forage. Others propose that sleep is when the brain consolidates memories, clears out metabolic waste, or repairs cellular damage. All these functions might be true, but they don't fully explain the mystery of why consciousness needs to periodically shut down. On a world with very different day lengths, would sleep evolve differently? On ancient Earth, with its shorter days, did early organisms sleep at all? Perhaps they had brief rest periods, minutes rather than hours. Or perhaps the rapid cycle of light and dark made sleep unnecessary, with organisms simply reducing activity during the brief nights. The lengthening of days might have actually driven the evolution of sleep as we know it. As nights grew longer, it became advantageous to have an extended rest period rather than trying to remain active in the darkness. Sleep might have evolved in complexity as days lengthened, adding stages and functions as more time became available for rest. Dreams themselves might be influenced by day length. Do we dream more during longer nights? Are our dreams different in winter versus summer? Some cultures that experience extreme seasonal variations in day length, like those near the poles, have rich traditions about the different qualities of dreams during the long polar nights versus the endless polar days. As we near the end of our contemplation, let's return once more to the present moment, to this very instant where you find yourself, perhaps preparing for rest. The earth beneath you is turning at precisely the rate that has allowed human civilization to flourish. This rotation rate, about 1,000 miles per hour at the equator, seems fast by human standards, but is actually quite leisurely by cosmic standards. You are lying on a planet that has been slowing its spin for billions of years. And this very moment, this exact rotational speed, is unique in Earth's history. Never before has Earth rotated at exactly this rate, and it never will again. This moment is the culmination of billions of years of cosmic evolution, and the starting point for billions more. Tonight, as you drift towards sleep, you might reflect on the profound journey that brought us to this moment. From the primordial nebula that gave birth to our solar system, through the formation of Earth and Moon, through billions of years of patient tidal friction, to arrive at this precise rotational period that defines our days. You are experiencing a moment that required the entire history of the universe to create. The calcium in your bones might once have been part of an ancient coral, growing in daily rings when Earth spun faster and days were brief. That calcium was forged in the heart of a dying star, expelled in a supernova, drifted through space for eons, became part of the nebula that formed our solar system, was incorporated into the early Earth, cycled through rocks and oceans and living things countless times, and now forms part of your skeleton. You are lying on a bed, on a planet, made of stardust that has been recycling through cosmic processes for billions of years. The iron in your blood has an even more dramatic history. Iron is formed in the final stages of massive stars, just before they explode as supernovae. The iron in your body has been through at least one, possibly several stellar death throes. It has been part of asteroids and planets, dissolved in ancient seas, incorporated into the earliest life forms, cycled through countless organisms, and now carries oxygen through your bloodstream. Every breath you take is powered by atoms that have witnessed the birth and death of stars. The water in your body, making up about 60% of your mass, has been on an incredible journey. Some of it might have arrived on Earth as ice in comets, pelting the young planet during the late heavy bombardment 4 billion years ago. It has been rain falling on primordial landscapes, ice locked in ancient glaciers, steam rising from prehistoric volcanoes. It has been part of countless organisms, from the first bacteria to dinosaurs to the tree outside your window. Water is the ultimate recycler, the medium through which Earth's materials flow and transform. Your DNA carries information that stretches back to the very origins of life. The genetic code, the language in which the instructions for building and operating living things are written, has been conserved for billions of years. The same basic code that operates in your cells operated in organisms that lived when days were half their current length. You carry within you a library of information about how to live on Earth, accumulated over billions of years of evolution. But you are more than just a collection of recycled atoms and ancient information. You are conscious, aware, capable of contemplating your own existence and the vast scales of space and time in which you exist. This consciousness, this ability to think about thinking, might be the universe's greatest achievement. Through you and beings like you, the universe has become aware of itself. Your thoughts about Earth's ancient 6-hour days are part of the universe thinking about its own history. Your wonder at the patient process of tidal friction is the cosmos appreciating its own elegant mechanisms. Your imagination of alternative Earths with different day lengths is the universe exploring its own possibilities. You are not separate from the cosmic story. You are the cosmos becoming conscious of its own narrative. The gentle pull of gravity that holds you to your bed is the same force that has been slowing Earth's rotation for billions of years. It's the same force that holds the moon in its orbit, that binds galaxies together, that shaped the large-scale structure of the universe. As you lie there, you're participating in the gravitational dance that connects all matter in the cosmos. Your breath, as you inhale and exhale, mixes with an atmosphere that has been dramatically transformed since those early days of 6-hour rotation. The oxygen you breathe was produced by organisms adapting to different day lengths throughout Earth's history. Each breath connects you to billions of years of photosynthesis, to countless organisms that captured sunlight and released oxygen, gradually transforming Earth's atmosphere from poisonous to life-giving. The nitrogen that makes up most of the air you breathe has its own story. Much of it has been in the atmosphere since Earth's early days, cycling through organisms and back to the air countless times. Some nitrogen atoms in your lungs might have been breathed by dinosaurs, by the first land plants, by the early animals that crawled from the sea. Breathing is participation in a conversation that has been going on for billions of years. Even the darkness gathering outside your window has a history. The night is only dark because the universe had a beginning, because stars have finite lifetimes, because space is expanding. In an eternal static universe, the night sky would be blazing with the light of infinite stars. The darkness of night is evidence of cosmic evolution, of a universe that changes and develops over time. The stars visible in the night sky are at different stages of their own evolution. Some are young, just beginning their nuclear fusion. Others are middle-aged, like our sun. Some are in their death throes, swelling into red giants or collapsing into white dwarfs. Each star has its own planets, perhaps its own stories of changing rotation rates and evolving worlds. The night sky is a gallery of possibilities, a display of the different paths cosmic evolution can take. Tomorrow, the sun will rise again, taking its familiar path across the sky. But it won't be exactly the same path as today. The sun is slowly drifting against the background stars as Earth orbits. The sunrise will be about 1/50 billionth of a second later than today, due to Earth's slowing rotation. These changes are imperceptible to human senses, but real nonetheless. Part of the continuous evolution of our cosmic environment. The moon will rise about 50 minutes later than it did today, continuing its monthly journey around Earth. It will be about 1/10 of a millimeter farther away than it was today, continuing its billions-year retreat. These tiny daily changes accumulate into the grand transformations that reshape worlds over geological time. As you prepare to sleep, you might wonder what dreams will come. Will you dream of ancient Earth with its racing sun and looming moon? Will you dream of future Earth, rotating slowly under a swollen red sun? Or will your dreams, like consciousness itself, exist outside of normal time, mixing past and future, real and imaginary, in the timeless space of sleep? Rest now, knowing that you are part of this vast, gentle story. The same forces that have shaped Earth's rotation for billions of years continue their work tonight. The moon continues its patient pull on Earth's tides. Earth continues its gradual slowing. The universe continues its expansion. And you, precious collection of ancient atoms, temporary pattern in the cosmic flow, sink into sleep, joining the rhythm of a universe that has been patient enough to wait billions of years for this exact moment, when you could exist, and wonder and dream about the time when Earth's day lasted only 6 hours. The boundary between waking and sleeping is like the Terminator line that divides Earth's day side from its night side. A gentle transition zone where consciousness fades into dreams. As you cross this boundary tonight, you're participating in a rhythm as old as complex life itself. A cycle of activity and rest that evolved in response to Earth's rotation. Sleep is Earth's gift to its creatures. A time for restoration and dreams, made possible by the reliable alternation of day and night. In the moments before sleep takes you, your brain waves are slowing, shifting from the rapid beta waves of waking consciousness to the slower alpha waves of relaxation, and soon to the theta waves of light sleep. This deceleration of neural activity mirrors, in its own small way, the deceleration of Earth's rotation over cosmic time. As Earth has slowed from 6-hour days to 24-hour days, so your consciousness slows each night from the quick thoughts of day to the deep rhythms of sleep. The stages of sleep that you'll cycle through tonight might have evolved differently on a planet with different day lengths. On ancient Earth, with its brief nights, perhaps organisms experienced compressed sleep cycles, achieving in 3 hours what we now spread across 8. Or perhaps they didn't experience the distinct stages of sleep we know, instead having a simpler, more uniform rest state, REM sleep. That strange state where our eyes dart beneath closed lids and dreams unfold in vivid detail might be a relatively recent evolutionary development, made possible by the longer nights that came with longer days. The complex architecture of human sleep, with its 90-minute cycles and distinct stages, might be a luxury afforded by our 24-hour days, a complexity that wouldn't have been possible in the racing days of early Earth. As sleep begins to embrace you, consider that you're not really still, even in rest. You're spinning through space at hundreds of miles per hour as Earth rotates. You're orbiting the Sun at 67,000 miles per hour. The solar system is circling the galaxy at 500,000 miles per hour. The galaxy itself is moving through space at over 1,000,000 miles per hour. Even in perfect stillness, you're on a cosmic journey through space and time. This motion continues as you sleep, carrying you through the night toward tomorrow's dawn. While you dream, Earth will rotate about 15 degrees per hour, steady and reliable. The moon will continue its orbit. The planets will trace their paths. The stars will wheel overhead. The cosmic dance continues whether we're conscious of it or not. A reminder that we're part of something much larger than our individual awareness. Your dreams tonight might touch on deep time without you realizing it. The human mind, even in sleep, processes the information it has encountered. The story of Earth's changing rotation might weave itself into your dreams in subtle ways. You might dream of flying, experiencing the freedom from Earth's gravitational bonds. You might dream of time moving strangely, faster or slower than normal, your sleeping mind playing with temporal possibilities. Dreams themselves exist in a different relationship with time than waking consciousness. In dreams, we can experience vast spans of time in moments, or moments stretched into seeming hours. We can be multiple ages simultaneously, can experience the past and future as present. Dreams might be consciousness's way of escaping the tyranny of sequential time, of experiencing something closer to how time might really be, all moments existing simultaneously, only seeming sequential to our waking minds. Some indigenous traditions speak of dream time not as sleep, but as a different kind of waking, an awareness of the deeper patterns that underlie everyday reality. In this view, when we sleep, we don't become less conscious, but differently conscious, aware of connections and patterns invisible to our waking minds. Perhaps in dreams, we sense the deeper rhythms of cosmic time, the patient processes that shape worlds over billions of years. As you sleep tonight, Earth's tides will continue their ancient rhythm. Somewhere, water is rising, creeping up beaches and into estuaries. Somewhere else, it's retreating, revealing the temporary landscape of the intertidal zone. These tides are Earth's pulse, driven by the moon's gravity, the same force that has been slowing our planet's rotation since the moon formed. The creatures of the intertidal zones will respond to these tidal movements, as they have for hundreds of millions of years. Crabs will emerge from their hiding places to feed. Barnacles will open their shells to filter plankton from the water. Seabirds will arrive to feast on exposed shellfish. This daily drama, played out on countless shores around the world, is a direct consequence of the Earth-Moon gravitational dance that has shaped both worlds. In the deep ocean, far from the land, the tides create currents that move vast volumes of water. These tidal currents help mix the oceans, bringing nutrients from the deep to the surface, carrying oxygen to the depths. Without the moon and its tides, Earth's oceans might be stratified, with distinct layers that rarely mix. Life in the oceans might be very different, perhaps confined to narrow zones where conditions are suitable. The solid Earth also responds to the moon's pull, though we don't usually notice it. The ground beneath you rises and falls by about a foot as the moon passes overhead. This solid Earth tide is happening right now as you prepare for sleep. The seemingly solid ground is actually flexing, breathing in response to cosmic forces. You're riding a wave of rock, a tide in the planet itself. These Earth tides affect things we might not expect. They can trigger earthquakes in areas where stress has built up along fault lines. They affect the precision of particle physics experiments, requiring corrections in the most sensitive instruments. They even affect the flow of time itself, as predicted by Einstein's general relativity. Time passes slightly differently when you're on the high tide of the solid Earth versus the low tide, though the difference is far too small to perceive. As night deepens around you, different parts of the world are experiencing different times of day. While you prepare for sleep, someone on the opposite side of Earth is waking to morning light. Someone else is experiencing the full brightness of noon. Others are watching the sunset. Earth's rotation creates this diversity of experience, this multiplicity of moments happening simultaneously around the globe. If Earth still had 6-hour days, this diversity would be even more pronounced. In the time it takes you to have dinner, night would have fallen and dawn would be approaching somewhere else. The human experience would be even more varied, with people constantly transitioning between day and night. International communication would be even more complex, with time zones changing rapidly. But in our current 24-hour world, there's a stability to the daily cycle that has allowed human civilization to develop its current complexity. Our agricultural systems depend on predictable day lengths. Our economic systems assume people work during daylight and rest at night. Our social structures are built around the rhythm of days and nights. We are, in a very real sense, a civilization shaped by Earth's current rotation rate. As you drift deeper towards sleep, your body temperature is dropping, your heart rate is slowing, your breathing is becoming more regular. These changes are controlled by your circadian rhythm, your internal clock that's synchronized to Earth's rotation. This biological clock is so fundamental that it continues even in constant conditions, without external time cues. Though it gradually drifts out of sync without the daily reset of sunrise and sunset, the molecular mechanisms of circadian rhythms are remarkably conserved across different species, suggesting they evolved very early in the history of life. The same genes that control daily rhythms in humans are found in fruit flies, in mice, in plants, even in some bacteria. This deep conservation suggests that adapting to the daily cycle has been one of the most important challenges life has faced throughout its evolution. Your circadian clock affects almost every aspect of your physiology. Hormone levels rise and fall in daily patterns. Cell division rates vary throughout the day. Even your immune system has daily rhythms, with different components more active at different times. You are not just living on a rotating planet. The rotation is encoded in your very biology, in the molecular clockwork of every cell. This biological encoding of Earth's rotation means that in a very real sense, you carry the day-night cycle within you. Even in the constant light of the Arctic summer or the constant darkness of the Antarctic winter, your body maintains its daily rhythms. Shift workers who sleep during the day and work at night often struggle because they're fighting against these deep biological patterns. As sleep finally takes you, remember that you're joining a rhythm that connects you to all of life on Earth. Every organism that has ever lived on this planet has had to adapt to its rotation. From the first bacteria to the last species that will exist before the sun expires, all are united by the shared experience of days and nights, of light and dark, of activity and rest. The Earth continues its patient rotation as you sleep, carrying you eastward at 1,000 miles per hour toward tomorrow's dawn. This motion is so smooth, so constant, that you feel nothing, like a passenger on a perfectly steady ship. The only evidence of motion is the wheeling of the stars overhead, the rising and setting of the moon, the inevitable approach of sunrise. In about 8 hours, the sun will rise again, its light touching your part of Earth after a journey of 8 minutes across the 93 million miles of space that separate us. That sunlight was born in the sun's core hundreds of thousands of years ago, slowly working its way to the surface through countless interactions with solar matter. The light that wakes you tomorrow morning has been traveling for longer than human civilization has existed. When that light arrives, it will start another day, one of the approximately 30,000 days in a human lifetime. Each day is precious, unique, irreplaceable. No 2 days are exactly alike, as Earth is always in a slightly different position in its orbit. The moon is in a different phase, the planets have moved to new positions. Tomorrow's day will be imperceptibly longer than today's, continuing the patient process that has been ongoing for billions of years. But for now, in this moment between waking and sleeping, you can rest in the knowledge that you're part of an ancient and ongoing story. The story of Earth's rotation is also the story of life, of evolution, of consciousness itself. It's a story written in stone and DNA, in the movements of celestial bodies and the rhythms of sleeping creatures. You are not just an observer of this story, but an active participant. Your mass contributes to Earth's moment of inertia. Your consciousness adds to the universe's self-awareness. Your wonder at the cosmos is the cosmos wondering at itself. You are the universe becoming conscious of its own patient transformations, its own deep history, its own promising future. As you cross the threshold into sleep, you might imagine yourself as part of a vast continuum of sleeping creatures throughout Earth's history. Billions of years ago, when days were brief, The first simple organisms experienced their own simple forms of rest. Hundreds of millions of years ago, the first complex animals developed true sleep, with distinct neural patterns and restorative functions. Millions of years ago, the first mammals dreamed beneath the stars, their sleep cycles tuned to the lengthening days. And now you, heir to all this history, carrier of ancient atoms and evolved information, prepare to add your own night's sleep to the countless nights that have passed on this rotating world. Your dreams tonight will be unique, never before experienced and never to be repeated. Yet they'll also be part of the eternal pattern of rest that has characterized life on Earth since sleep first evolved. The moon watches over your sleep as it has watched over countless sleeping creatures throughout Earth's history. Its gravitational pull continues the patient work of slowing Earth's rotation, ensuring that days will be slightly longer for your descendants than they are for you. This is the moon's gift to the future. Time itself, parceled out in ever so slightly longer days. Somewhere in the cosmos, on other worlds orbiting other stars, other beings might be settling into their own rest cycles, timed to the rotation of their own planets. Some might experience days lasting minutes, others days lasting years. Each world has its own temporal rhythm, its own dance of light and dark. The universe is filled with countless variations on the theme of planetary rotation, each creating unique conditions for whatever might live there. Perhaps on some distant world, creatures are experiencing something like Earth's ancient 6-hour days right now. They would know no other rhythm, would be perfectly adapted to their rapid cycle of light and dark. To them, our 24-hour days would seem impossibly long, our nights stretching like eternal darkness. We are each adapted to our own cosmic circumstances, each perfectly suited to our particular moment in our planet's evolution. As your consciousness fades into the mysteries of sleep, the universe continues its patient work. Stars are being born in distant nebulae, their rotation rates determined by the conservation of angular momentum, just like Earth's was billions of years ago. Planets are forming around young stars, their initial spins wild and chaotic, gradually settling into stable rotations. Moons are forming or being captured, beginning their own patient work of tidal evolution. Somewhere, a planet's day is lengthening by its first millisecond. Somewhere else, worlds are becoming tidally locked, their days synchronizing with their years. The process that has shaped Earth's rotation is happening throughout the universe, each world writing its own story in the language of angular momentum and tidal friction. The universe never sleeps, never pauses in its patient evolution. While you rest, galaxies continue their stately rotation, taking hundreds of millions of years to complete a single turn. The universe itself continues its expansion, space itself growing, carrying galaxies apart like raisins in rising bread. Dark energy continues its mysterious acceleration of this expansion, shaping the ultimate fate of everything. Yet in this vast, evolving cosmos, this night's sleep is not insignificant. It's part of the pattern, part of the story. Your rest tonight is enabled by billions of years of cosmic evolution that produced a planet with just the right rotation rate for complex life to flourish. Your dreams tonight are made possible by the patient slowing of Earth's spin from those ancient 6-hour days to our current gentle pace. Sleep now, cradled by a planet that has been preparing for this moment since its birth. Let Earth's rotation rock you into dreams, knowing that you're held by forces that have been operating for billions of years and will continue for billions more. You are safe in the embrace of a cosmos that knows how to be patient, that never rushes, that allows every process to unfold in its own perfect time. Let your thoughts dissolve into the timeless space of sleep, where past and future merge, where the 6-hour days of ancient Earth and the tidally locked future Earth exist simultaneously in the eternal now of dreams. Rest in the knowledge that you are part of something magnificent, ancient, and ongoing. A cosmic dance that began with the birth of the universe and will continue until time itself ends. The story of Earth's 6-hour day is not just a tale of the past, but a reminder of the constant change that characterizes existence. Nothing is permanent, yet nothing is truly lost. Energy and information transform but persist. The rapid spin of young Earth has become the measured rotation of today and will become the slow turning of the far future. Each stage is perfect for its time, each moment a unique gift of cosmic evolution. As sleep finally claims you completely, you join the rhythm of the cosmos itself, the patient pulse of change that drives all evolution, all development, all growth. Your breathing slows to match the deep rhythms of the universe, where changes are measured not in heartbeats, but in eons, where patience is infinite and time is abundant. Dream well, child of the cosmos, heir to billions of years of patient change. Tomorrow you will wake to a world imperceptibly different from today, continuing your journey on a planet that has been finding its perfect pace since the very beginning. But tonight, rest in the eternal present of sleep, where all of Earth's days, past, present, and future, exist in the timeless moment of now. The universe holds you gently as you sleep, continuing its ancient dance, its careful balance of forces, its slow transformation of everything into everything else. And in your dreams, you might visit Earth as it was, with its racing 6-hour days and looming moon, or as it will be locked in its final configuration, or as it is right now, perfectly poised in its cosmic evolution to cradle sleeping consciousness and dreams of deep time.